Hi, my name is Jean, and I'm happy to present our work with the title Predator, a model for pairwise point cloud registration with deep attention to the overlap region, on behalf of my collaborators Shengyu, Mikhail, Andreas, and Konrad. Point cloud registration is typically divided into three steps. In the first step, the interest points are sampled and their local neighborhood is described using high-dimensional feature descriptors. In the second step, these feature descriptors are matched to establish the putative correspondences. Finally, the optimal rotation and translation are obtained by robustly minimizing the L2 distance between the correspondences. Recently, there has been a lot of progress achieved in point cloud registration, and on the popular 3D-Match benchmark, state-of-the-art methods already seem to be saturated. However, by taking a closer look, it can be observed that the performance deteriorates rapidly when the relative overlap of the input point clouds is reduced. This is not reflected in the traditional benchmarks because they only consider high overlapping pairs. It does, however, represent a problem, as being able to robustly register low overlap pairs is important for applications such as scene reconstruction and LiDAR SLAM. There are multiple possible reasons for performance drop in low overlap regime. For example, due to the large receptive field of modern deep networks, the local features could be contaminated by irrelevant local context. However, by sampling fixed ratio of interest points in overlap region with FCGF features, we are still able to recover the performance drop for low overlap pairs. This hints at a problem that most interest points are sampled outside the overlap region and do not even have a correspondence. This motivates us to develop an overlap attention module which can guide sampling to the overlap region. Conventional registration pipelines use an encoder-decoder architecture to extract the local feature descriptors without sharing the information between the point clouds. But this co-contextual information is crucial to reason about the overlap regions. We therefore propose an overlap attention module that lies in the bottleneck. It starts with a self-attention graph neural network to further aggregate local context. The two sets of superpoint features are then mixed in the cross-attention module to learn co-contextual information and the overlap scores. Finally, a second self-attention graph neural network is used to further smooth out the conditioned features and overlap scores. The superpoint features and overlap scores are then decoded to the point level using the decoder network. We train our model using three loss terms: the circle loss for feature learning, and the weighted binary cross-entropy loss for overlap and matchability scores. We start our evaluation by investigating if the overlap attention module helps increasing overlap ratio. To this end, we compute overlap ratios between point cloud pairs with and without our overlap attention module. As can be seen in the top figure, our overlap attention module succeeds in predicting the overlap regions and hence increases the overlap ratio. This can also be observed in the bottom figure, where as desired, the curve denoting the overlap obtained with our attention block decays slower. We proceed by evaluating different ways of sampling the interest points given the overlap and matchability scores. Specifically, we compare top K sampling with the probabilistic sampling, which samples interest points proportionally to the product of the scores. As shown in the top figure, top K sampling leads to clustered interest points and less accurate registration due to small baseline problems, while probabilistic sampling is more robust. As shown in the table below, both overlap-informed sampling methods outperform simple random sampling, with probabilistic sampling performing the best in most cases. We evaluate the registration performance of our method on three datasets: 3D-Match, Odometry Kitty, and ModelNet. Predator sets the new state-of-the-art on 3D-Match and Odometry Kitty, while on ModelNet achieving comparable performance to RPMNet that is specifically tailored for object-centric datasets. Further qualitative results show that our method robustly predicts the overlap and matchability scores and estimates accurate poses using probabilistic sampling in combination with the RANSAC estimator. For more details, please check our project page or consult our paper. If you have further questions or want to discuss general 3D vision problems, please also feel free to contact us directly. Thank you for watching.